So let's go over 7.3, simplifying radical expressions. So we're going to use and introduce the product rule and do a few exercises using the product rule. So again, I remind you, this is called the nth root of a. The n is the index and the a is the radicand. I just call it the value under the radical, or the number under the radical. I seldom myself use the radicand, others do. So if the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b is equal to the nth root of a times b. And we can actually easily show that, because if you recall, the nth root of a is equal to a to the 1 over nth power. And the nth root of b is equal to b times the 1 over the nth power. So a to the r power times b to the r power is equal to a times b to the r power. So a to the 1 over the n times b to the 1 over the nth is equal to a times b to the 1 over nth, which we can just simply write as the nth root of AB. So it really just follows from other rules we have that connect the nth root to fractional powers of A. Here is the thing that I want you to make sure you keep in mind, that in order to use the product rule for radicals, the index of the radical signs have to be the same. So the value, you'll actually be given a value here. The value given for n has to be the same. So let's do a few exercises. So remember, when no radical is written, it's assumed to be 2. So the square root of 3 times the square root of 5 could be, if we really wanted to write it that way, is our radical, our index is 2. The number under the radical is 3. Our index is 2. The number under the radical is 4. So by the product rule for radicals, this is just the square root of 3 times 5, and that's equal to the square root of 15. So let's do 1b. You should try to mimic this on your own. So again, we were using the square root, so the value of the index is assumed to be 2 times the square root of x is equal to the square root of 21 times x. There's nothing that can be done to simplify that. Why? Coming over here, noticing 21 is equal to 3 times 7. Now, so writing it out that way, 3 times 7. If we ever had 21 or some number equal to a list of primes, a product of primes, raised 2 powers, if we can actually simplify. And I think we'll see this right here in our next example. So now our index is 3. So we can say the third root of 4 times the third root of 2. Well, that's equal to the third root of 4 times 2. But note that 4, we're looking for multiples of 3 in powers. 4 is equal to 2 times 2. So I'm replacing 4 with 2 times 2. Then I'm multiplying it by another 2. So this is the third root of 2 to the third. And since our index is odd, we can actually simplify this even more. Now, I'm not for sure if they actually do the simplification. But that's equal to 2 to the third raised to the 1/3. So that's just equal to 2. So it's not plus or minus, it's just equal to 2. And that's because the index is odd. So 2 times 2 times 2 is equal to 8. And that's what it means for the nth root of something to be that value. Recall, if, going back just to the definition of the square root. So the square root of a number b is some number c such that, st stands for such that, c squared is equal to b. So now let's use the nth root. The nth root of b is equal to c whenever, just using a different term other than such that, whenever c to the nth power is equal to b. So again, the third root of 2 to the third, well, if c is equal to 2, then c cubed is equal to 2 cubed. So the answer there is just plain old 2, not plus or minus 2, just plain old 2. 1d. So the fourth root of 5y squared times, again we have the same index, the fourth root of 2x cubed. So the index is even, so we'll keep that in mind. So just using the product rule, that's the fourth root of 5 times 2, which is 10, y squared x cubed. And there can be no simplification. That's all we have. Now the last one, 1e, we have the square root of 2 over a times the square root of b divided by 3. So we're literally just going to use the product rule. So this is the square root of 2 over a times b divided by 3. And make sure when you do this that you extend the radical symbol all the way over so that it includes the numbers under the radical. So the final simplification needed here, 2 over a times b divided by 3 is just simply 2b divided by 3a. And that can't be simplified at all. So let's look at the next page. We're going to be given another rule. It's the quotient rule. And you could have almost anticipated it, because really what we're doing is we're using the same rules that we used when the index was 2, when we had the square root. And we're just extending those same rules so when the index has a different value. So again, we're talking about quotients. So we're talking about some number a divided by another number b. That means b can't be 0. We always state that. It's just a habit. It's an important habit in math. I've actually seen papers written by non-mathematicians, philosophers usually, that try to prove something using math, and they forget to check if their denominator is 0, and they prove things that don't follow because they don't check, and indeed the conclusions they actually arrive at don't follow because explicitly the denominator is equal to 0. And you can't do that. Mathematicians are trained differently, that's for sure. By the time you get to grad school, you're trained quite a bit to always check to see about division by 0. So the square root of 25 divided by 49. Again, just using the quotient rule, which you already know because the index here is 2. So the square root of 25, so we always take the positive root, is 5. And the square root of 49 is not 9, but 7. So this is pretty simple, pretty basic. The point with you taking this at home is you can't let yourself get bored. You can't let yourself be distracted. That means when you sit down and you watch these lectures, you've got to do it at a time that works for you. So this is just a direct application from this step to this step here. It's just a direct application of the quotient rule, but I can simplify the square root of 9. So I'm going to go ahead and do that. The square root of 9 is just 3. So the cube root now of 8 divided by 27. Well, that's the cube root of 8 divided by the cube or the third root of 27. Either way is fine. Now in our previous example, we just learned that 8 is equal to 2 to the third. So I'm going to rewrite 8 as 2 to the third. And as it turns out, 27 is 3 times 3 times 3. So it's 3 to the third. So that's equal to 2 thirds. (2d). The fourth root, that's even. So we would always just take the positive answer if there is any. You'll see what's going to happen here. So that's equal to the fourth root of 3. That cannot be simplified. That's an irrational number. At the bottom is the fourth root of 16y to the fourth. So let's think about what is 16. 16 is equal to 2 to the fourth. So that's times y to the fourth. So bear with me. I'm doing this in steps. You're okay to skip some of these steps. Again, we've already stated that the numerator cannot be simplified. But using just the regular exponent rules, 2 to the fourth times y to the fourth is 2 times y to the fourth. So we're almost ready for one last simplification. So again, this is the fourth root, the square root of 3. So since this is the fourth root of something raised to the fourth, when I take it outside of the radical, I have to make sure it's positive. Now the problem is I don't know whether y is positive or negative. If it's negative, when it's raised to the fourth, it's going to become positive. So I don't have to worry about a complex root here. So in order to assure that we get a positive value, we put it in absolute value signs. And there's one last simplification here. And these are simplifications that I think my math lab will make you do. So since 2 is positive, it's 2 is always positive. I can take it from in between the absolute value signs. So it's 2 times the absolute value of y. And that's the end of that one. So let's do some more simplifications. So these simplifications are going to require some factorizations of the numbers inside them. So let's look at 3a. So by the numbers inside, I mean the numbers under the radical. So let's come over here and let's factor 50. Well, 50 is clearly 5 times 10. And 10 is clearly 5 times 2. So 50 is equal to 2 times 5 times 5. But another way of writing that is 2 times 5 squared. So that's what I'm going to write over here. Notice, remember, my unstated index here is always 2. So I'm taking the square root. I'm not writing 50 as it is, but rather this way, 2 times 5 squared. So here we have, since my index is 2, I have a power raised to an even power, something that is divisible by the index. So I can take this whole component, 5 squared, outside, but the price I have to pay to move it on the outside of the index, or outside of the radical symbol, is to divide its existing power by the index power, which is 2. So that equals to 5 raised to the first power times square root of 2. So that's kind of how we're going to do these. 3b. So here we have the third root of 24. So the first thing we have to do, we don't really know, can it be simplified or not? Let's come over here and let's factor 24. I always just start with the easiest thing to divide it by, the thing that pops to my head first. And in this case, that's going to be 2. You could use 6, that would be okay as well, but it's going to be 2 for me. So that's 2 times 12. Now 2 is prime, so that branch of the tree is done. However, 12 can also be divided by 2, and I get 6. But 6 can also be divided by 2, and I get 3. So 24 is equal to 2 times 2 times 2, which is 2 to the third, times 3. So I'm going to write this as the third root of 2 to the third times 3. So here I have an exponent under the radical that is divisible by the index. So that means I can move it out from underneath the radical. The price for doing that is I have to divide the existing exponent, which is 3, by the index value. The 3 has to stay underneath there. But 2 raised to the 3 divided by 3 is just 2 raised to the first power, which is just 2 on the square root of 3. And sorry, I need to bring down the fact that this is my radical index is 3. It's really easy to forget to bring that down. We're habituated to just write the square root symbol, but that's an important bit of information. And in a way, it kind of is a call to say, hey, stop using the square root symbol, use the square root symbol and the index, but that's never going to happen. Mathematicians are humans too, and they get set in their ways just like humans, all humans. So again, my index here is 2, so this is 26. So what I have to do is come over here and let's factor 26. So again, the first thing I see is it's divisible by 2. It's 2 times 13. So I don't have any powers. Both of these are not to powers that are evenly divisible by our index, which is 2. So done. There is no further simplification. It is as simplified as it can be. So now our index is 4. We're going to do the 4th root of 32. So let's come over here and factor 32. I'm going to divide it by 2. That gives me 16. I'm going to divide 16 by 2. That gives me 8. Divide 8 by 2 and it gives me 4. Divide 4 by 2 and it gives me 2. So these are all primes. So 32 is equal to 2 raised to the what power? 1, 2, 3, 4, 5. 2 to the 5th. So this is equal to the 4th root of 2 raised to the 5th. Now here's the thing. If you have a power, an exponent, under the radical that is larger than the index, then what you need to do is to subtract numbers until you get a number that is evenly divisible by the index. So what I'm going to do here is I'm going to write 2 to the 5th is 2 to the 4th times 2, because 5 minus 1 is equal to 4. So I have to do 2 to the 5 minus 1 times 2, and that's equal to 2 to the 5 minus 1 plus 1, which is equal to 2 to the 5th. So I have my equality. So now what can I do? If you didn't understand what I did over there, it's a little math trick that we do. If you expect sometime to really like math and major in math, it's for those people. For everyone else, just ignore it. So what can I do? The exponent here is greater than 1, and it's divisible by 4. So I can move 2 to the 4th outside. Now to move it out from underneath the radical symbol, I have to divide its power by the index. And of course, this factor of 2 has to stay underneath. So 2 to the 4 divided by 4 is just 2. Remember, I need a 4th root right there. So it's 2 times the 4th root of 2. And so just remember to copy down your index. It's a really easy thing to forget, but without that index there, the default is that you're thinking that the index is 2, but it's not, it's 4. So when it's any number that's not 2, we are obliged to write it down. So here's something that you want to, this is a page you want to include in your notes. So when is a radical simplified? So in general, we say that a radical of index n is simplified when all factors of the radicand raised to the nth power have been removed from inside the radical sign. Every factor. So that's what we've actually been doing, and here's kind of the more technical definition. So it's a really good idea that you remember this list of perfect squares. 2 squared is 4, 12 squared is 144. You already probably memorized these in high school. When I was in high school, we didn't go beyond 10. We just had to remember 10 squared. And it's kind of embarrassing. If I'm not mistaken, for our multiplication tables, we quit at 10. We didn't have to go beyond 11. I mean, we didn't have to go to 11 or 12. I think it's standard practice now that you go all the way to 11 and 12. but I could be wrong. It's been a long time. Perfect cubes, 1, 8, 27, 64, 125, and perfect fourth powers. So the fourth power of 256 is 4. The fourth power of 81 is 3. The fourth root of 256 is 4. The fourth root of 81 is 3. The fourth root of 16 is 2, and the fourth root of 1 is 1. So we're going to use that information to simplify. Again, the only real game we have in town is the product rule. So I'm adding absolute value signs. It seems to me one of the objections I have to this particular book is that they teach you about the absolute value sign, which I introduced to you in either the lecture before this or the one right before this. And then they get to 7.3 and they forget all about it. Or they hedge their bets and say, pretend all values of x are positive. So if all values of x are positive, you don't have to worry about the absolute value sign. And that's just malarkey. So 25, we should know already, is equal to 5 squared. So remember, our unwritten index is 2. So that's 5 squared times x squared. So that's equal to the square root of 5x squared. So when I move this out from underneath the radical sign, I have to divide the existing exponent. And when I move it out from underneath, we leave a factor of 1. Now, the square root of 1 is 1, so I really don't even have to bother to write that. But I'm just going to show you it didn't disappear. There's no magic. I'm still using the exact same pattern before. The only difference here is when I've moved it out, I don't know if x is positive. So technically, this is equal to 5 raised to the first power times the absolute value of x times 1, because the square root of 1 is 1. So its actual answer is 5 raised to the absolute value of x. But I think in your homework, they state something along the lines, assume all variables. Now you'll have to check me on this. You see the homework are positive. So if I already know that x is positive, then the answer that you would enter in here would just be 5x. And you wouldn't need the absolute value sign, because the absolute value sign doesn't do anything to a number if the number is already positive. So this is 4c. So we're on fourth roots now. So that list of fourth roots will be really, really good for you. So 81 times z to the 11th. So I hope the obvious thing that you're going to do here now is rewrite 81. Just look at the notes I just gave you. Is 4 raised to the fourth power. But what about z to the 11th? I need to subtract some values of 11 so that I get to something that is divisible by 4. So 10 is not divisible by 4, 9 is not divisible by 4, but 8 is. So I'm going to write this is z to the 8th times z cubed, because 8 plus 3 is 11. Now what do? We take these factors that are raised to exponents that are powers of 4, we can take them outside. In each case, we have to divide the existing exponent by the index 4. Again, I have the 4th root here in z cubed. So this is equal to 4 raised to the first power. And this is equal to z, 8 divided by 4 is squared. And that's going to be, you don't have to put parentheses there, times the 4th root of z cubed. I messed up, didn't I? So for those of you who are waiting for me to catch my mistake, I was concentrating on the power there. 81 is equal to 3 to the 4th. And I just wrote 4 to the 4th, focusing on the fact that it was raised to the 4th. Sorry about that. So let's go through and just replace everything. 3z squared. Now, I don't have to worry about absolute value signs, and like I said, I don't think the book makes you worry about absolute value signs. But in this case, I wouldn't need it anyway, because no matter whether z is positive or negative, z squared is going to be positive. So the absolute value of some number squared is just z squared. They're always identical. So 4b. So now my index is 3. So 54 x to the 6th. 6 is divisible by 3. That's kind of nice. Y to the 8th. It's pretty easy what I can do to change that so it's divisible by 3. But I need the factorization of 54. Well, 54, I'm going to divide it by 2, and that's equal to 2 times 27. And let's look at our third roots. 27 is equal to 3 to the 3rd. So this is equal to 3 to the 3rd times 2. So that's exactly what I'm going to do when I start my simplification. 54 is 2 times 3 to the 3rd times x to the 6th. So what can I do to get y to the 8th? Well, 8 is clearly greater than 3, so that means I can do something. If I subtract 2 from 8, I get 6. So I can write y to the 8th is y to the 6th times y. So I'm just going to dispense with the absolute value signs from now on. And what can I do here? Three to the 3rd can come out, but its existing exponent has to be divided by the index, times y to the 6th, that can come out, but it has to be divided by 3, the index. I forgot x to the 6th. X to the 6th can come out, but it has to be divided by 3. And what's left in there? Just my 2 and my y. I just have to remember to write my index here. So 3 to the first power is 3. Y to the 6th divided by 3 is y squared. X to the 6th divided by 3 is x squared. So that's the third root of 2y. And they would probably, and it's annoying, and you all know more about that than me, they would probably want you to write this as 3x squared y squared times the third root of 2y. They should not require that. We have plenty of symbolic tools that can easily determine that y squared times x squared is the same as x squared times y squared. And bonus points for anyone else who might see yet one further simplification of this. Going all the way back to our exponent rules, it seems like it's been forever now. This is the same thing as 3 times x times y using the power of a product rule squared times the cube root of 2y. I think they're okay with this one. I would certainly be okay with that one on an exam. I would not expect that final step. Because that final step is more of a kind of your subjective preference. And this is one thing I'll tell you. I will never count off for a subjective preference. Now, you've already experienced the fact that I've required you to do some work using a specific method I taught you. Now, that wasn't because of my subjective preference. It's because online symbolic help does not do it that way. So by me forcing you to do it that way, I'm assured you're not using something on your screen that I can't see, and in essence using illegal tools and getting grades that you shouldn't be getting because you didn't study to get those grades. I would be happy to give it to your computer. So 81 again is 3 to the 4th by the list we just saw, and z to the 11th I'm going to write as z to the 8th. Seems like I just did this one. Did I just do this one? I'm getting deja vu here. So at any rate, this is 3 to the 4 divided by 4 times z to the 8 divided by 4 times what's left inside. That's not 11. That's 3. Sorry. Talking too much here. I'm trying to figure out if we really and truly just did this one, and yes, we did. So that's 3z squared times the 4th root of z cubed. I don't know why I did that one twice. Whatever. Maybe it's deja vu. Maybe it's a Mandalorian effect or whatever. Mandela effect. I don't know what it's called. So now we're going to be using the quotient rule. So basically, it's kind of like in music. I've introduced a theme, which is a rule in this case, and we're playing variations on that theme or themes. So what problem is this one? This is 4. So this is 5a. So the square root of 20 divided by the square root of 5. So we're going to do the other direction. This is equal to the square root of 20 divided by 5. And you should always go this way if the radicand in the numerator is divisible evenly by the radicand in the denominator. So that's equal to the square root of 4. And you all know that one. That's equal to 2. So the square root of 50 divided by 2 and the square root of 2. So what's going on here? There is a little bit of something going on here. So that's the same thing as 1/2 times the square root of 50 divided by the square root of 2. Well, that's equal to 1/2 times the square root of 50 divided by 2. Do you see how this is going to work out? Well, that's equal to 1/2 times the square root of 25, which is equal to 1/2 times 5. One half times 5, which is equal to 5/2. And now I look up at the problem and I see I forgot to copy down a value of x. So I'm just going to go ahead and put it in, and that's going to require a slight modification right here. So let me erase, sorry, apologize. See if I can't get my eraser to be bigger. We'll start right here. I'll fix it starting right there. So this is again 1/2. It's a little bit thicker there. 1/2 times, here I go, the square root of 50 divided by 2, 25x. Well, that's equal to 1/2 times the square root of 5 squared times x. So I can bring, since 2 is divisible by the index, that's equal to 1/2 times 5. The x has to remain underneath the radical. So another way of writing that is 5 times the square root of x divided by 2. Sorry about that, I copied it down wrong. So here's a doozy, or so it seems at first. I'm going to suggest it's not going to be near as bad as it looks. So this is example 5C. So I'm going to challenge you right now to see what you can do with number 7. Just kind of look at it. You notice that the index is 3. Now y on the denominator, let's see what you can do there. So you're going to use the quotient rule. Since the indices are the same, you can use the quotient rule. Come back here. So let's just do it. I mean, you can pause and do it on your own. So this is 7 times the cube root of 48 x to the 4th y to the 8th over the cube root of 6y squared. So let's just literally use my index rule first. Let me 7 times one big huge index thingy. It's the index is one huge radical, and the index is 3. So that's going to be equal to 48 x to the 4th y to the 8th divided by 6y squared. So let's go ahead and simplify this out. I'm hoping you're seeing what I'm seeing. It's going to be far easier 48 divided by 6 is 8. X to the fourth stays to the same. Y to the eighth divided by y squared is y to the sixth. Now recall that 8 is equal to 2 to the third. So I have 7 times the cube root. I'm going to write 8 is 2 to the third. I'm going to write x to the fourth is x to the third times 1. X to the first. There we go. And I know I can do that because 4 is greater than 3. And y to the sixth I don't have to do anything to, because 6 is evenly divisible by 3. Now I'm almost ready. I'm going to bring some stuff out. So that requires me to scoot this 7 over. And each thing that I bring out, 7 is going to be multiplied by it. So 2 to the third divided by 3 is 2 to the first. Now I can bring out x to the third. X to the third divided by 3 is x. Y to the sixth. 6 is divided by 3 is y squared. And what has to remain? Just this one factor of x. So it's the cube root of x. So 7 times 2 is 14. X, y squared times the cube root of x. Okay, that's it. We don't do the distance and midpoint formulas. That is not part of what we do in intermediate algebra. You'll do that in college algebra. So from here on down, as far as the notes go, you can absolutely ignore them. And I'll write a little note here just in case you're going through fast forward. I'm just going to say ignore midpoint, and I've changed your homework to not include midpoint or distance problems. Okay, that's it for 7.3.